VCSELs are a type of semiconductor laser diode. Because of their optical and physical characteristics, they're often used as light sources in mobile and other devices in applications such as face and gesture recognition, range finding for autonomous vehicles and UAVs, augmented reality displays, just to name a few. These new applications involve devices generally powered by batteries, so power consumption becomes a major issue. Characterization of the beam emitted by the VCSEL in all these applications, including power measurement, pulse shape, as well as beam profile and other parameters, is critical. However, when we go about trying to measure VCSEL beam power, for example, we run into a few serious challenges. 1. The beams are generally widely diverging, so we'll need a sensor that can handle difficult beam geometry. 2. The beams tend to be pulsed, with low pulse frequency and low duty cycle. This means we're faced with low average power, but at the same time high peak power. Two separate problems result from this. First, the low pulse frequency can beat with the sampling rate typical of laser power meters. For example, a typical Ophir meter samples a power sensor's signal at 15 Hz. If the VCSEL is pulsing at, say, 10 Hz, the readout will suffer from a 5 Hz beat frequency that'll make it very difficult to get a proper reading. Secondly, here we see what a low average power but high peak power signal might look like. Let's think about this for a moment. What power scale do we set the meter to? If we choose a scale appropriate for the average power, as we normally do when measuring power of CW beams, then we're looking at a low average power scale, meaning high gain in the electronics. But then, when the pulses come, the detector will saturate, which can lead to a measurement error. If, on the other hand, we want to avoid saturation, and so we select a scale appropriate for the high peak power, meaning low gain in the electronics, then we'll be operating near the floor of the scale and will suffer from poor resolution and lots of noise. In other words, any scale we choose will be wrong. Ophir offers a comprehensive set of solutions for accurately measuring VCSEL beams. Let's see how each of these challenges we just looked at is taken care of. 1. Widely diverging beams. Ophir's IS6 family of integrating spheres with integrated power sensors and fully calibrated covers powers from a few hundred nanowatts up to 30 watts, depending on the model, over the spectral ranges relevant for VCSELs. There are configurations for collimated as well as diverging beams, in fact even for very widely diverging beams. This model, for example, the IS6D IR170, has a specially designed input port that gives it an acceptance angle of over 170 degrees. A range of accessories makes it easy to optimize the configuration for the most accurate measurements. For example, magnetically attachable apertures to eliminate unwanted reflections from the PCB on which the VCSEL is mounted. Additional ports enable sampling light from the sphere to other measurement instruments, such as fast photodetectors for pulse shape analysis, spectrometers, and so on. 2. High peak power with low average power. The new low-frequency power mode, supported by a number of Ophir meters and PC interfaces, takes care of this. The sampling rate is adjusted to match the actual pulse frequency, which the user's prompted to enter. No more beat frequency. The gain is lowered and the resolution is increased so that we get accurate measurements of the low average power without being thrown off by saturation caused by the high peak power. Here you can see a measurement of a slowly pulsing beam in regular power mode and in low frequency mode. To learn more, contact Ophir directly or via your local Ophir representative, or visit our website.